So welcome to the Picture Language Seminar. Next week, we'll have one more talk, a very special talk by Zhengwei Liu. He's going to brainstorm in mathematics and physics. And then we'll have a pause and resume in January. And the first talk on January 5th is by Renato Renner. So today, we're really pleased to have Gian Michele Graf. He's an expert in many fields of mathematical physics. He started with spectacular results on asymptotic completeness in scattering theory in 1990, and she's worked on stability of matter, quantum Hall effect, topological insulators. He's now the head of the theoretical physics group at the ETH, and will tell us today about topology and shallow water waves, a violation of bulk edge correspondence. So welcome, Gian Michele.
Shall I share the screen at this point? Okay. So there we go. Let me move this out of the way. Good. So good morning, everybody. I would like to thank Arthur Jaffe for inviting me to his mathematical picture language seminar. I feel very much honored, and I'm very happy to be there with him, at least virtually. So I'm going to report on some work done with two of my collaborators, Jud and Tauber. It's going to be soon appear in CMP. And it is inspired, though, and yet at variance with some work by Pierre Delplace and John Marsden and Antoine Venay that appeared recently in Science. Well, conclusions will be somewhat different. So here is a brief outline. I'm going to say what bulk edge correspondence is. Probably many of you know already. To those I ask for forgiveness. Then I will introduce a hydrodynamic model on which then I will illustrate this correspondence, or rather its violation. And I would have to show why there is topology, and this will be achieved by compactifying the model in a certain sense. Then I will come back to this bulk edge correspondence once again, define the edge index again, just for clarity, sorry for the repetition. Then we'll see in detail what the violation is all about. And then finally, if time allows, to see what actually goes wrong and why there is a violation. So this is the mathematical picture language seminar. So I think I owe Arthur a picture. I'm not sure it's a mathematical picture. It's a famous woodblock print by Hokusai called The Great Wave of Kanagawa. What you see here are some boats amidst of big waves. And at first you think that there are waves all the way to the horizon, but that is not quite true. You see the hand. So what you see there is Mount Fuji, which means that there is a coast somewhere. And this picture somewhat illustrates the interplay between oceanic waves and coastal waves. what the talk is about. So what is bulk edge correspondence? Not specific to this model, but in somewhat more general terms, and then which I then shall make more precise. So a topological insulator, and I mean at first one that is infinitely extended, also known as the bulk, shall have an excitation gap above the ground state. Now, if you put an edge to the system, so if it has an edge, then at that edge, there are gapless excitations with energies in the bulk gap mentioned just before. And so here is the picture. You have a gapped bulk in blue, bordered by a gapless edge. And more precisely, the topological property of the bulk and the edge are supposed to match, to have this bulk edge correspondence, by the way, also called bulk boundary correspondence in some circles. And in this talk, I would like to give you a counterexample, that is present a topological bulk model which is not matched by its edge. Now, I've stated it as a principle, and principles, are as such not yet true or false, but I still claim that honestly, this is a counterexample. Of course, you may at the end of the talk have a different opinion, and say that the principle was never intended in the sense of the counterexample, but I must leave that to you. So let's make that bulk edge correspondence a somewhat slightly more precise statement. Let's take a geometry in which the bulk, after having put an edge, fills a half plane. So the upper half plane, and the edge is this infinite horizontal red line. Let's also suppose that the problem has a periodicity in both x, horizontal, and y, vertical direction, at least as long as the bulk is infinitely extended in all directions. Once you put the edge, of course, you break the translation in the y direction. That's why I've crossed it out. Let's talk about the energy. When you still have the whole bulk, then you have two translations, x and y, and you have two momenta, okay? Two momenta, horizontal and the vertical one. And now let me talk about the spectrum. And I shall assume that we have a problem with a single particle spectrum. This is definitely somewhat a simple situation, but let's consider that one. Now the energies are in that case a function of these two momenta, horizontal and vertical. Once we put the edge, we can no longer speak of a vertical momentum, but what we can still represent the spectrum as a function of the longitudinal momentum and just lump together all energy values obtained at different value of the transverse momentum. And for each value of k, which is still a good quantum number, I get an interval of values, of energy values. And that interval changes as the longitudinal momentum changes, and it sweeps out a band like the one you see in this picture. So that's the spectrum of the infinite bulk. And when you cut it to a half plane, then additional spectrum is added, and this is the edge spectrum shown in red. Again, at the fixed value of k, the longitudinal momentum, these are individual points, which, however, then move as a function of it and give rise to this curve you see here. So some of these, let's follow one of the upper rim of the blue band. There are, like at the position of the hand, some edge eigenstates which leave the edge just to return. But there are others which leave for good and join some band higher up or from the lower rim further down. And let's introduce a number, which is n plus, say, when talking about the upper rim. And let's count how many leave minus the number of those which join, right? So there is a relative sign, and that is n plus for the upper rim, and similarly n minus for the lower rim, except that we change the relative sign in what we count positive and what we count negative when going from the upper to the lower rim. One little point that will be helpful later, if we say are at the lower rim and it's the lower rim of the lowest band, then there is no way where these eigenvalues could go further down, and all eigenvalues which leave the rim will join it n, and that would mean that n minus is 0, if this is the lowest band. Now, having said that, one can make a precise statement about bulk edge correspondence. There are many, but this is one precise one, and it's due to Hatsugai. He developed in a specific model, but it's somewhat more generally valid. And how does it go? On the left-hand side, you see something blue, which is attached to the bulk. And in fact, you go back to the eigenvalues of the bulk I mentioned before, which are a function of both momenta, but you look at the eigenvectors, and the eigenvectors, as k moves over the torus, the eigenvectors sweep out a vector bundle, which has a Chern number, which is a Chern of p. And this is claimed to be equal to a property of the edge, that is the number of edge states leaving the upper rim minus the one joining the lower rim, n plus minus n minus. So that is the statement. And there is a corollary or a slight restatement, which is perhaps better known. Suppose now you have two bands, which you see here, and suppose these bands are the bands to be occupied by fermions, and you have a Fermi energy somewhere, which is in the gap. So the band J is the highest occupied band, the J plus 1 is the lowest empty band. And as you see from the picture, the number of edge states leaving J plus 1 from below is the same as those joining the J band from above. So this is this equation here. And it's also the same number n sharp of eigenstates crossing the Fermi energy mu. And as a result, bulk edge correspondence can also be phrased like this, that n sharp is equal to the sum of the Chern numbers, not of one band as before, but of all bands that are below the Fermi energy. And this is immediate corollary of what I said before, because by expressing the Chern number of each band, as I explained on the previous slide, as a difference of contributions from two rims, then by the equation you see here in the middle, that sum is actually telescoping, and it just leaves the upper contribution of the rim of the upper rim of band J, which is the same as crossing this, crossing the Fermi level, minus what you have at the very bottom, which however is 0. Hence you have this bulk edge correspondence in this form. But whenever in doubt, and we shall be in doubt, it is better to go back to the previous formulation, which is tailored to a single band, like here. Okay, so this we just put aside, and now let's come to the concrete hydrodynamic model. You may like it or not like it. It's a take it or leave it proposition. And here are some assumptions before I write down any equations. The Earth is rotating. That can hardly be disputed, so sure. The Earth is flat. Well, this is more problematic, but locally certainly yes, and that's the point of view we should take. And the sea covers the Earth. That is worrisome, but don't despair, we'll sight land. And you know, this sentence seems to me it's a little bit of a metaphor of the situation we are going through now. The virus covers the Earth, but we shall not despair because we shall sight land. And in fact, the sea is shallow, and technically this shall mean that the depth of the sea is small compared to the wavelengths. So it's all a matter of perspective. Now here are the equations which describe the model, and not just defining the model physically, just explaining what the equation is so far. Later the physical explanation. So we have two dynamical fields. One has two components, and it's just a horizontal velocity, which depends on two coordinates x, y of the plane. And there is a height above average, which is eta, function of x and y. These are the dynamical quantities. And then there are a number of parameters. There's the gravity, the acceleration of gravity. There is an average depth h. There is an angular velocity. I write f over 2 for that. And there is something I'll explain, the odd viscosity nu, invented in a sense by Yossi Avron. You don't just see the vector field v, you also see v perp, which is the same vector field once it is rotated by 90 degrees counterclockwise. So that much for the notation. And here is a sort of a quick derivation of the physical meaning of the equations I just presented. It's basically just mass conservation and momentum balance in the shallow water approximation. So again, the typical wavelength is much bigger than the average depth. I forgot to say something at the beginning. Whenever you have questions, just butt in. Don't be afraid. Are there any questions so far?
If you hold the space bar, you can unmute yourself.
If I
Okay,
hold
can you hear me?
Yes, I hear you.
Okay, so the question is why horizontal velocity? You have generally you have velocity in arbitrary direction.
So yes, we have in principle in a basic model the velocity has two horizontal components on a flat Earth and the vertical component. In the effective description, the vertical component is eliminated. this was the final effective description you see on this slide. And I may say something about your question in this slide, which is about the derivation.
Okay.
So if it's not satisfied at the end, then you'll ask me again. So here you have the horizontal velocity components, and we assume that the fluid as a three-dimensional object is incompressible and therefore has a constant density rho. Now this vector field V underscore nonetheless is not divergence free. It has sinks and sources simply because this fluid can pile up in the third direction and change the height Z, right? And therefore the area density is rho times that height Z, and that area density is not constant, and which matches the fact that this vector field is not divergence free despite the fluid being incompressible. And so if you write the equations in terms of this two-dimensional object, the first equation is just the continuity equation for this area density. So this is this d by dt is the so-called material derivative, the derivative as perceived from an object flowing with the fluid. And in this shallow water situation, you can just imagine, and you see it with your eyes, the fluid moves basically in horizontal direction and just very little in vertical direction. And moreover, the horizontal velocity has no z dependence in this shallow water limit. And so this is the correct continuity equation. The other equation is another Euler equation, essentially Newton's equation. You have the mass rho z times the acceleration dv by dt is equal the force, and there are various forces, body forces F, and the divergence of the stress tensor sigma. So the body force itself has two parts. One, which is the gravity minus gradient gravitational potential, which is that of a column of water of height z, that goes with c squared. Then there is the Coriolis force, which is proportional to v, but actually perpendicular to v. So that's why we have this v perp, and goes with the rotation frequency f. And then we have the stress tensor sigma, which has a notation that needs to be explained. In any event, this is the odd viscosity. So to the notation, given a vector field u, you can introduce the shear velocity du, which is the traceless symmetrized gradient of u. Usually, in the Navier-Stokes equation, one would use as the shear viscosity, the shear velocity of the velocity field. And that results in a divergence, which gives minus mu Laplace v. That is the usual term you see in the Navier-Stokes equation. But here we do it differently. We do not insert the velocity field itself. We insert its rotated version. And by doing so, it remains dissipationless, unlike with the usual viscosity, which is dissipative. That way it remains dissipationless. You have a factor 2 mu in front, which I guess just comes from the 2 mu you have also downstairs here. And it is weighted with this z because that's the thickness of the fluid. So now everything is explained. And you have to do, please.
Little v and little u, are these the same things?
V and so this little u, nice to hear you, Jörg. This little u here is a generic vector field u, which you can replace either by v as you would do in Navier-Stokes, or as with v perp as we do here.
Good, thanks.
Okay, so we are not yet done, but quite. One sets the height z of the fluid equal to an average height h plus a small deviation eta, fluctuation eta, and you linearize in that fluctuation as well as in the velocity field, which is small anyway. And then, it's not going to the derivation, but you can believe me that out of the equations I physically motivated, you get basically the equation you saw on the previous slide. Now after division by some parameters, the viscosity is called nu rather than mu. And then by setting some quantities, dimensionless values, G and H become equal to 1. And then you're back to the equations before. One last point on this slide, why the heck do we introduce this odd viscosity there? It gives an ultraviolet completion to the model. You see, when you introduce this new, then the highest derivative in the equation is this one, this Laplacian, which comes with the new. The origin of it is in this odd viscosity. And so even though at moderate momenta, this is irrelevant if nu is small, at high momenta, it changes the model, and it changes in a way that makes it topological, as we shall see. So here are again the equations of motion. Now we want to rephrase them in a way that is more suggestive even, and this is due to, it's related to quantum mechanics. Let's split up the horizontal velocity in two components, u in the x direction and y in y direction, introduce momenta for the derivative, px and py, and then collect the three components of the field, that is eta, u, and v, into a column vector which we call psi. And then after multiplying the equations by I, this gets the form of the Schrödinger equation, I d psi dt, with this Hamiltonian you see here at the bottom. It is self-adjoint. You know, this wouldn't have been for a regular viscosity, but the odd viscosity keeps it, and also the Coriolis force, the fact that this dissipation less is important for this to be self. Now, how do we get a topology into the picture? So here is again the Hamiltonian. The only thing I noticed here is that we have translation invariance, so we can, momentum is a good quantum number, and the analysis of H reduces to fibers at fixed momenta called K with components Kx and Ky. And so we have to diagonalize this matrix for a fixed K, which is easy. And in fact, it is the problem of a spin one particle, so to speak. And here is the spin one in an irreducible representation with components S1 and S3 are shown here. And this matrix is just a linear combination where you dot this vector S you see here into some vector D. And the components of this vector D can be read off explicitly here on the right? And you may notice that when K is large, this term with the odd viscosity is the dominating one. But if K is moderate and U is small, it's not so important. So the eigenvalues are immediately computed. They are 0 and plus or minus the length of this vector. Plus or minus the length of this vector. You see it here, these are the eigenvalues omega plus and omega minus, and the length is easily computed, and you see it there. So here is what we just had on the previous slide, and let me just plot these eigenvalues. Certainly not plotting omega 0 equal to 0, but let me plot omega plus. Omega minus is then the opposite. So here I plot it as a function of R2 of K in the plane R2. Now you should view this as a surface of revolution around the vertical axis. And it looks a little bit like a parabola because it's a parabola at small value of K. And it is another parabola at large value of K because eventually under the root it goes like K to the fourth, but once you take the root, it's another K squared. And then, so that's for the bulk, but then we want to introduce the edge. And before even talking about the edge spectrum, we want to get rid of the momentum Ky, which means we project the surface of revolution in the Kx, in the Ky direction and label it still with Kx. And so this means that this surface of revolution gets, or this parabola better, gets filled in by these red values here. The model has a gap. There is one eigenvalue at 0, which is just this horizontal line. And then there is this omega plus, and its minimum value is taken at K equals 0, and it is F. So it's the Coriolis force, which makes sure that the model has a gap. So the eigenvalues I discussed, let's also say something about the eigenvectors. And just for the upper band, omega plus. Here is the Hamiltonian again, d dotted into S. The eigenvectors do not change if I pass to the unit vector E, right? And so these are, the eigenvectors do not change if I pass to the unit vector. And let me call as ket E the corresponding eigenvector for the positive eigenvalue. And that's just the one of a spin 1 particle, j equals 1 in its highest magnetic number, m equals 1. Now this vector E changes from point K to another one in the plane, right? According to what's written up there. It's just the unit vector which is associated to it. But to this, let me have some remarks before continuing the discussion. So first, let me just point out that the 1-point compactification of the plane R2 is the 2-sphere S2. Now, when you look at this vector D first, here it is again, and you ignore this odd viscosity, and you go all the way to infinity, then you see that this vector takes up all possible directions, depending the directions you take to go to infinity. But if you put that odd viscosity in, when you go to infinity, this just points down, so to speak, in the third direction, because this is the dominant term. And so if you go to the corresponding unit vector, this has a well-defined limit as k goes to infinity, regardless to the direction you took, right? As a result, this direction, E of k, is defined not just on the plane, but it extends to the 1-point compactification, S2. And so you end up with a map from the compactified plane, S2, to S2 itself. And that map, even by the expression here, wraps the sphere once. You can see that because at least it wraps the sphere once if f is positive and u is positive, because when k is equal to 0, well, then these points, when k is equal to 0, then you just have a third component, f, points, so to speak, north. And then when k gets larger, it touches all longitudes. And when k goes really large, you go to the south pole. So you wrap, the sphere wraps itself once. And here is a lemma. You're not so much interested in the sphere, but in the eigenstate ket E, which is associated. Let's assume that the product of these two constants f and u is positive. And we are looking at the line bundle defined by ket E, defined on that sphere. And I claim that the Chern number of that is 2. That's very easy. So let's even give a proof. So if the particle would not have been a spin 1, but the spin 1/2, then if you look at the ket E on the Poincaré or the Bloch sphere, then in fact it's given by E again. So the map is just the identity. And therefore the wrapping of that map is 1, as I illustrated before. Now, the particle is, however, a spin 1, but the spin 1 up particle can be obtained, or spin 1 up state can be obtained as part of the triplet, as the spin up for the 1/2, for the spin 1/2 tensored with itself. And now the Chern number is additive for tensor product of line bundles. And so the result is 1 + 1, which is that 2. Okay, so this just shows that once you compactify the model, it has this topological nature, and it has a very nice topological number. So before starting the talk, I saw that Marianne Leitner was in the audience, and I should say that she has some early work, which you could even say is somewhat a precursor of that, but if I'm not wrong, there was no compactification. So here there is a compactification, and there is a bulk index as a result. So another thing I would like to mention here is that first, that if you change, say, f, the sign of f, then the Chern number would not be 2, but it would be -2. And the other thing is that this model is not just, completely out of the blue. This is something you can observe. Because if you, let's move on, if you go from the northern hemisphere where the Coriolis force has one sign to the southern hemisphere, then you change the topology of this bundle, and therefore you have an interface, and like at edges, you're supposed to see some interface states. And indeed, they are seen from the satellite. So here you see two views of the Pacific Ocean, differing in time by about 1 month. And what you see in red is a height above average, by just a few inches though, but the positive height above average, which within a month moved east by quite a bit, right? So there are these edge states moving along the equator, and they move, unlike other states which do not move, like this feature here. It's still at the same spot essentially, or they move less at least. They clearly, these interface states clearly move in a definite way. So now I've told you about first just the bulk problem and the bulk problem and the topology which is associated to it, but we have to bring the coast into the picture. And so here is a little analogy. You know, if you have a particle subject to a magnetic field in the plane, it goes on cyclotron orbit like this, except if it intercepts the boundary where it has these skipping orbits. And this is somewhat like with these waves, which under the Coriolis force have a motion like that one, but at the coast start developing a different behavior. And so it is really nice to see that Bert Halperin was in the audience. I just saw him before. And of course, he was perhaps the first one having this picture in mind. And he realized that these boundary waves are gapless at the beginning of the 80s. It is, however, a fact that Kelvin knew it about his waves about a century earlier. And so Halperin's work had far-reaching consequences in a whole field, without which we wouldn't have topological matter as we know it. And I would just also bring Kelvin into the picture here. So here is again a short repetition of edge index and bulk edge correspondence, since we had it at the beginning of the talk. Let me just go through pretty fast. So quite generally, restricting the system to a half plane produces states with energies in the band gap, and the edge index is associated with those states. Here is basically the picture we saw before, and we have these green edge states now. And you can, this is maybe worth pointing out, you can see them in various ways. You can see them as states moving along the edge. You can see them in regard to their behavior as you move away from the edge, and then there are evanescent waves, they decay exponentially into the bulk. But you can also fix the longitudinal momentum k, and then they start having the mathematical appearance of bound states. And then you can define an edge index as the signed number of edge states traversing the gap, as shown with the dots in this picture here. And the bulk edge correspondence is that the edge index is the same as the bulk index of all bands below, regardless of the boundary condition. This is important, regardless of the boundary condition, because you know, if it's supposed to hold for any boundary condition, then it cannot depend on it because the bulk has no knowledge of boundary. And this is what we would like to probe now. So sighting land, let's have a look at the edge model. We restrict our system to the upper half plane, and we need to put some boundary conditions on our triple of fields, eta, u, and v at y equals 0. There are plenty of self-adjoint boundary conditions. I'm not considering them all, but I'm also not considering just one. I'm considering a one parameter family of such to see whether for which parameters it may, correspondence may hold and for which it may not. Here is the boundary condition. It takes two suitable conditions to make a self-adjoint boundary condition. Here is the parameter A, right? And so this is a pair of boundary conditions that defines a self-adjoint operator, but other ones are possible too. They are not considered here. And they may give rise to even other phenomena not fully explored yet. But let's look at one value of A, 0.75, and then at its spectrum. So here in light blue, you see the spectrum I showed before as a function of the longitudinal momentum kx. So you have this parabola field in above, one below, and there is the flat band at omega equals 0, which is shown here. In yellow, you have the edge states. So there is this edge state with a constant slope and another one which has not a constant slope. Now, if we were to take the recipe of putting, so to speak, the Fermi energy somewhere, the number of intercepts would depend on the somewhere. It's 2 here and it's 1 there. So it's why I said at the beginning, when in doubt, let's go back to the original approach of Hatsugai, which is to follow exactly the rim of the band and to see how many edge states emerge from it. In this picture here, 1 emerges from the lower rim of the upper band. And bulk edge correspondence would predict, however, that the signed number n minus of eigenstates emerging from that band is 2. Now, in principle, there is also an upper rim of that band here. But since that band reaches all the way to infinity, there is no real upper rim. And so we are just left with the lower rim and its count n minus, which in this figure gives 1, whereas the Chern number of the bulk is 2. And so you would say we are facing a violation. Let's examine the problem somewhat more slowly. But before that, let me just say that, you know, all these things have names. So there are these edge states with a constant slope, which go back to Kelvin. There are these other edge states with a non-constant slope, Yanai waves. There is this flat band of bulk states called Rossby waves. And there is all the rest, which are the Poincaré waves. Not so important. But let's go slowly through different values of A to have a picture of what happens. So here is a somewhat negative value, A equals to -4. And here, what do we see? We see 3 edge states emerging from the rim. Now here it's somewhat hard to distinguish, but in fact there are 2 emerging, and there is 1 merging here. So 3 minus 1 gives 2, and everything is fine because that's the Chern number. So let's move on to a slightly bigger value of A. So here in the finite region, not much has happened, but this edge state, which formerly merged here, has moved, the merging point has moved out at infinity and has disappeared. And the problem is back, because 3 is not the same as 2. And then here is 1 more. So here, no big change with respect to -2, just the distinction becomes clearer. And the second, the wave next to the Kelvin waves has become steeper. And if we, you know, I showed 3 at the time, so the one before is now in the middle and the new one has joined. So these edge states have yet a steeper slope. Then by the time it was 0, the slope is vertical, which is something very funny. It's not even clear whether such a thing should count as emerging or disappearing. How do you count that? Right here, it's still emerging. Here, you don't know. And when you go a little bit past, then it's disappearing. I see there is a chat contribution in the chat. Let me see what it says. I hope it doesn't come back.
Marianne or Werner now.
So what are the defect indices of H? So they are 1 and 1. Sorry, no, 2 and 2. 2 and 2. That's why you need 2 boundary conditions to make a self-adjoint operator. Good. And then, yeah, but I mean, the question I think just arrived when this vertical line was shown, and it will be clarified. And because it's against what the self-adjoint operator can do, but we'll see. And then, so we are now at 0.25 here, and then No, it doesn't. Sorry, I should. It doesn't. I have to stop the share a second. No, now it works again, I think. Okay, good. So here are the last three values we saw, and here there are these Yanai waves which start to become flatter at 0.75. At A = 1, they merge with the Rossby waves. They're not seen anymore. And when you go past, they re-emerge from the other side. And then not quite finally, but at 2, you see again a merging point or leaving point which has come in from infinity. It is here. And when you go to slightly larger values, this point moves in towards the origin a little bit more. And now I think we have enough samples. And let me just go through the last ones again. So this was the last one. And let's summarize what we've seen. We've seen Kelvin waves in all cases, but also that the bulk edge correspondence is violated. And there are edge states never merging with any band, like some of these Yanai waves. And there are states merging at infinity, you could say. For instance, this one, this leaves at this point, but stays close to the rim. And in some sense, at infinity, it merges back to the band. And here is the summary of the values which are obtained. It's just based on the picture, but actually it can be proven. And it represents, in a sense, the main result here, the violation of the correspondence. That is that as a function of the parameter which rules about the boundary condition A, the edge index takes the values, well, when it is very negative 2, then when you make it a little bit larger 3, then it jumps to 1, and then finally it is again 2. And this should be compared with the bulk index, which is always 2. Now, maybe depends whether you want to accept this as a violation or not. But one objection one could make is that maybe you should consider such a curve like this one, not just as a departure here, but also as a merger at infinity, and modify the count at infinity. But the problem with that is that if you modify the count here for A = 2, then you're going to spoil actually a case where you do have correspondence. A = 2 is in this situation here, and you do have correspondence, and so you may not want to change the definition because it would just spoil the case, which is okay. So still some time, but I think 50 minutes or so. I'm not quite sure I can give you the full explanation of what goes wrong, but let's give it a try. Here is again the statement that n minus the number of states emerging from the rim should be equal to 2, which is the Chern number. Good. Now, how can we relate the two things? We can relate them by doing scattering. And here is how we do scattering. We take the coast, which is this black thing, above is the sea, and we take plane waves out there in the ocean and send them towards the coast. That's an in-state. And then, there is some boundary condition here, and it will affect the scattered state out. And so this is the interplay between the oceanic waves and what happens near the coast. So this defines a scattering map. I mean, implicitly encode the boundary conditions is encoded in a scattering map, which is the map from in to out. And you can also define a scattering phase, which is a number then, which is the inner product between the in state and out state. I have to be a little bit more precise about this later on. And it is a function of the longitudinal momentum. So you still have K, and you also have omega, which is the energy. And you have to make sure that you are in a regime where you are above the threshold, so that you have propagating states in the bulk. So omega has to be larger than omega plus. So here is again the statement. And now this relation, which is basically a statement of Hatsugai, never mind whether true or wrong, can be split in two, as has been discovered by some years ago. One is to say that the Chern number is actually the winding number of the scattering phase, and I have to explain what this is. And the second one is that the winding number of the scattering phase is equal to the number of edge states joining the rim. And so even if you don't understand yet what this phase of the what this winding number of the scattering phase is, just by eliminating it from the two equations, you get the Hatsu-Guise state. So here is how you do it. You have this longitudinal momentum K, which in the original situation was on a sphere, and it will still be on a sphere, K, and you explore scattering at an energy slightly above the threshold by epsilon. And then you follow that as you move along that circle, and it acquires a winding number. For a generic function, f from the circle to the circle, and f is the winding number. So that makes clear what the statement here is. And so if the thing up here fails, it can fail in one of two ways. One of these two equations fails. And you can ask, what goes wrong? Is it that the Chern number is no longer the winding of the scattering phase? And I can, given we don't have much time, let me just jump ahead and tell you, no, that will stay. So here is the sphere of momenta K. The one, it was the plane, but I compactified to a sphere. And there is the marked point at infinity, which is here. And there is the meridian ky equal to 0, which separates the incoming states, have negative ky, from the outgoing states, which have positive ky. So, is this, yes. Okay, so this is what I just said. You have the incoming states and you have the outgoing states. Now, on this, on the hemisphere of the incoming momenta, you choose a section of your line bundle, psi in of k, or for short, in. And then you don't have to choose another section on the opposite hemisphere, because it's the scattering matrix which takes care of it. Sorry, the scattering map. To each in state, you associate the out state, which corresponds to scattering with given boundary conditions. So you also have a section on the blue hemisphere defined that way. It is important to say that it is impossible to choose a global nowhere vanishing section of eigenstates everywhere, simply because the bundle is not trivial. Right? That is the abstraction. But we could choose it, the red hemisphere, we could choose it a little bit more than hemi, a little bit more than half. In fact, choose it defined like this, actually anything except 1 point. So yes, the whole sphere except 1 point would do, but that is certainly good enough. And then this overlaps with the blue hemisphere, and there we may make a comparison along this shaded line, a comparison between the out state, which I've defined, and the in state, which is now defined on a little bit larger hemisphere. And for these momenta on the dashed line, both states are defined. And they can define a scattering phase that is just a number by taking the inner product of these two vectors which reside in the same fiber. And then you have this number, it is non-zero, and its winding number is n of s. So you wind around this all the way close to infinity, to the point at infinity, which is this one, but not quite. And so you realize that S, seen that way, is just a transition matrix between two local trivializations. So that suffices to say that the winding number of that 1-by-1 transition matrix equals the Chern number. So that is fine. And let's give it the green check mark like here. What is not fine is the other part of it. So that n of s should be the n of s, which is something computed slightly above the rim, above the threshold, because you do scattering, should be equal to something computed slightly below the rim, because these are the number of states which join it. This equality is, in Hatsu-Guise case, is or can be granted by Levinson theorem. And it's not that Levinson theorem is going to be wrong, but the hypothesis, the applicability of Levinson theorem is no longer going to be given. That is the short answer to what is wrong. Now, I'm not quite sure whether I can still find the time to explain that. Let me see how far I can get. So here is a somewhat more general situation. Suppose quite general that you have a Hamiltonian that depends on some parameter k, that you have a threshold above which you have continuous states and below which you have discrete state which move with k, and at some point k star you have a merger. So what does Levinson theorem say? I mean, this particular variant of Levinson theorem, it says that if you follow the argument of the scattering matrix slightly above the threshold, but between k1 and k2, so a point before the merger and the point after, well, that is going to, is the phase along such an interval here, very close to the threshold, is going to turn by plus or minus 2 pi, depending on whether an edge state is merging there or not. That is the statement of Levinson theorem. And to get an idea why it is true, we should go to the structure of the scattering phase. It can be written as the quotient of two functions, the Jost functions. And what you see here is that, well, first you have kx, which is the longitudinal momentum, which plays a passive role. Then there is the energy at which you do the scattering. And to that energy corresponds to two momenta, an incoming momenta ky tilde and an outgoing momenta ky of the same energy. And typically, if E is even there, these two momenta are equal and opposite. And the Jost function G, taken at these two momenta, is are analytic functions of ky. And a bound state, and so scattering state, yes, scattering phase tells you something about scattering, as the name goes, but it also tells you something about bound states through analytic continuation. So a bound state of the Hamiltonian at parameter value kx corresponds to a pole of the scattering amplitude at the value, at an imaginary value of the outgoing momentum, which is positive. And you know, the short way of saying is that you have a bound state without having an in state. But if this has a pole, this means that G, the Jost function in the denominator, has a zero. That will be an important thing. It is a short proof of this, but I'm going to skip it. And so here is again the picture of a state, now in this case being born at the critical value k star. And what happens is that the zero of the Jost function is first in the lower complex half plane, and so it does not correspond to a bound state, it corresponds to an anti-bound state, then goes to the upper half plane, imaginary upper complex half plane of ky, and then the zero is there, and there it corresponds to a bound state. So as kx crosses this critical value, a bound state appears. That is one part, that is one fact in this, which is associated with this picture. And there is a second fact, which you see when you look at the scattering phase. And in particular, let's look at the numerator. So ky tilde is the incoming momentum close to threshold. Take it negative but small. And the argument of that G, you see sort of given by this green arrow. You position, you evaluate the function at the blue point, but the zero is at the red point. And so except for an overall phase, this is the phase of G. And now if this red point crosses to the upper half plane, as it does when kx crosses the critical point, the green arrow turns, and it turns by minus pi. In the denominator, it's similar, but there you look at it from a point on the other side, so it turns by pi. And since this is not the product, but the quotient, the scattering phase S winds by 2 pi. So there are these two facts which go along. A state appears just below the threshold, and the scattering phase turns by 2 pi or minus 2 pi just above the threshold. That is basically Levinson theorem. And now I think really, for the sake of time, I'm not going to tell you what happens in the general what goes wrong to the ultimate detail. But let me just say this: at all points kx or k star, actually k star, where an edge state merges or leaves the upper band, like the one you see here, something like this happens. Something like this happens. But when you look at what happens when a state merges at infinity, or even when it does not merge at infinity, when just nothing happens, there are always such zeros crossing the horizontal line in the complex half plane. But the complex half plane is not just a plane, it is actually a two-sheeted Riemann surface. And therefore, more complicated things can happen there. And in fact, in such a way that it's no longer like in the Levinson scenario, but actually opposite. When nothing happens, the scattering phase changes at infinity. And when something happens, that is an edge state merges at infinity, then the scattering phase, in fact, does not widen. It's just anti-Levinson behavior. And that is, this opposite behavior is in a sense the explanation of what goes wrong. So let me just skip all these details. So here you would see the two sheets and how these things merge and move. And this is all a little bit complicated. But let me just go back to the final, to the theorem once again, where you see these values. And so here is a situation, this alternative, I could not go into these detailed situations, but I think I can summarize it nevertheless. Here you see that there is an edge state which departs here and merges again at infinity with the bulk band. But this is a situation where there is no exactly a non-Levinson behavior. There is no winding of S there, and indeed the count done in the finite of the phase of the scattering phase just matches the Chern number because there is no contribution coming from the point. In this situation, we see that there is a deviation, a violation of bulk edge correspondence, but there is also no edge state merging at infinity. And that's exactly when the S matrix at infinity actually turns on that two-sheeted Riemann surface. And when you, so this is what, so sorry, this, and then, so let's see here, we have 3, here you have 1, and you have also a violation. There is no edge states at infinity. And so the S phase does turn, but this time it doesn't turn by -1, it turns by +1, which reestablishes the total of 2. And finally, in this situation, A equals 4, where we have again bulk edge correspondence, the edge state merges again at infinity, but exactly because of that, there is no winding of S there. So that's the summary of how these things happen. And let me maybe just have one comment. Comment about what happens here at A equals 0. You know, you have this edge Hamiltonian HA, and you can fiber it according to Kx. This gives the edge Hamiltonian fiber by fiber. And the general theorem tells you that the fibers are also self-adjoint, but more precisely, it tells you so for almost all value of Kx. It's an almost all theorem. And what now happens when your parameter is 0, and also your longitudinal momentum Kx is 0, this is an instance where that Hamiltonian at this single point Kx fails to be self-adjoint. You know, this is within the cards. It's okay. Still, the whole edge Hamiltonian is perfectly self-adjoint. But it means this, that the boundary condition, which is one of the two boundary conditions, which reappears again here, if you say Kx equal to 0 and also A equal to 0, this boundary condition becomes non-existent. And therefore, instead of having 2 boundary conditions, you're left with 1. And for that particular value of Kx, you're not filling in the defect indices appropriately. And that's how it comes about, that this single Hamiltonian may have a vertical interval in its spectrum. In fact, it is not self-adjoint, even though the whole Hamiltonian, HA, not fiber, is self-adjoint. So here is the summary, slightly over time. The shallow water model has edge states in presence of Coriolis forces. The model is topological if compactified by odd viscosity. The model violates bulk boundary correspondence. And scattering theory of waves hitting the shore clarifies the cause. And Levinson theorem does not apply in its usual form. That's a summary of it, and I would like to thank you very much for your attention.
Well, thank you very much, Gian Michele, for a very interesting talk. And I'm sure there are many experts in the audience who have something to contribute to the discussion.
Okay, so I'm not an expert, but I have a question nevertheless. Usually surface waves are nonlinear waves. So for eta you have the nonlinear equation.
Well, depends what your model is. I did not cheat. I mean, sorry. Let me go.
It's a Newton's equation plus the boundary conditions. So it's an Euler equation or whatever.
Can you repeat?
Well, it's usually Newton's equation plus boundary conditions.
Well, it's in a sense it's Euler's equation,
right?
Of which Newton is part, indeed, and so Euler's equations are indeed nonlinear. No question about that. Even the continuity equation, strictly speaking, is nonlinear because you have both Z and you have V, right? Which makes it quadratic. But the point is that you linearize for shallow waves. So, okay. Sorry, okay. Yeah, shallow waves eta. And if you know, this is not wrong. You saw this picture from the satellite of the Pacific Ocean. H is several kilometers deep, right? H, but this eta was just a few inches. So the linearization is sort of appropriate.
So in a long, let's say, is a stable under nonlinear perturbations? I assume that for a long time, on a long time intervals, I can assume that the linearity becomes more important.
This is an interesting question, of which I only have a conjecture as an answer. So here is, let's again see what happens here in situations like this one. So you have edge states like this yellow one here, and in the linear situation they correspond to perfectly stable waves. If it's nonlinear, then you can ask, does it become a soliton? You know, from a distance, and I'm somewhat conjectural here, it looks to me, to first approximation, like a nonlinear focusing Schrödinger equation. You are at an energy below the threshold of the continuum, right? And that would make it stable. But on the other hand, there is a band below, which is like having a defocusing Schrödinger equation, nonlinear Schrödinger. And so I think that even though this might look stable for quite some time, ultimately you might have a non-stable edge state. But again, this is a conjecture.
But for soliton, you need Galilean invariance.
Good point. Which is not given here because there is a distinguished rest frame.
So it may be staying.
Well, remains to be investigated.
Right.
So I wonder, Bert, you were an early person on this problem. Do you have any comment?
Oh, I think it was a beautiful talk, and I need to digest it a little bit more. I wasn't familiar with Levinson's theorem, and I need to think about that one a little bit, but it certainly is very pretty. I guess this odd viscosity, obviously, in trying to apply it to real fluids, it works fine at small wavelengths, but then obviously real fluids don't usually have an odd viscosity. They have the even viscosity, and then that complicates matters. And I'm trying to think how that works. This point where you had the vertical, the one thing I'm puzzling about a little bit more is the place where you had the vertical line. That was, I guess, at your A equals 0.
Yes.
And that one, did that also depend on having the odd viscosity, or
Indeed,
phenomena?
It does depend on having the odd viscosity. Correct.
So that's something that doesn't occur in real hydrodynamics, as far as you know. I mean, there's nothing like it.
So I would think it does not occur. Correct. Yes.
Okay, that helps. Helps.
But you know, what is the purpose of this odd viscosity? Let me go back a little bit here. You could stay with the problem as it is defined here without the red term. And in fact, this is what this gentleman, Del Blas and collaborators did. But in this case, even though they claimed, the model is not really topological as such, because there is no unique limit. And so the fiber bundle, the vector bundle, is not defined on a compact manifold, but on an open manifold, and a non-compact manifold. And so, you know, there is no real Chern number. Now, you may still integrate up the Berry curvature, and lo and behold, you get 1. But it's a bit of an accident, right? It's not that you have a compact manifold and you have the Chern number.
Right.
Well, that's very interesting. Marianne, did you have anything to say?
Of course, you could get also half if the unbounded.
Yes. So how would you get the half?
No, well, that's
by taking
the infinite sum over ones with changing sign. So
so you would take another regulator, or 1/2 of what, actually? Because in a sense, 1 is 1/2 of 2. Yes. I'm not quite sure. You made similar considerations, I think, on the lowest Landau level in magnetic system, where there, in some sense, it's 1, but you may also turn it into 1/2 by looking at it for the Dirac equation. I think maybe you get 1/2, right? Rather than 1. Is this what you have in mind, or?
Yeah.
Yes. And so here it's not 1/2 of 1, but it's 1/2 of 2. Right? And which is an unfortunate circumstance, because if you get 1/2, you start worrying that it's not quite the Chern number. But if you get 1/2 of 2, you may think it still is an integer.
Mm-hmm. Mm-hmm. Thank you. Thanks.
Thank you.
Maybe I might have a question.
Yes, Jörg.
So if you apply this to hurricanes, in other words, you look at localized vorticity, say on the northern hemisphere, then I guess these problems will not show up. I suppose there you have a bulk boundary correspondence. Is that right? At least that's the way it always looked to me.
So I mean,
so you have a sink of pressure and air circulating around this sink, and then because of the Coriolis force, you get, something like a quantum Hall system, except that the magnetic field is replaced by the Coriolis.
Yes.
Is that in your equations, or is that something that needs to be analyzed separately?
Probably not, but I'm still trying to see where you are heading. So, so you want, where do you see the Chern number? So the Chern number, isn't the band flat in the situation you have in mind? That's what I'm suspecting.
Maybe the band is flat, but what you certainly have is something like a system that resembles a Hall fluid on a disk.
Yes.
So the boundary of the disk is where the pressure of the air rises. And then the air crawls along that edge because of the Coriolis.
Yeah, that for sure. I mean, that you have bulk states and you have edge states, that for sure. But the question is whether in all circumstances they come with the right numbers.
That's what I would have guessed, but I'm asking you. You are the expert. I'm the one who asks the question.
So what is the right number? The right number can be established for the bulk only, at least in this case, after a suitable compactification, I would say.
Yes.
And so I'm not sure this is in whether you can define a bulk index without that in your problem.
But how is it in your equations? Is there a term that describes the pressure that I could vary and make inhomogeneous? You see, I would like.
There is no pressure term. Why is there no pressure term? Here is why there is no pressure term. In a sense, the pressure is the gradient of the gravitational potential U. Right?
Mm-hmm.
I think the role of the pressure here would be that there is a tendency for the fluid to go where the height is higher to where the height is lower. And that is provided by this minus gradient U. I'm not sure this matches what you have in mind with pressure.
Not quite, no. It's not quite. But you would agree that the phenomenon of hurricanes is very much related to what you discussed.
Of course, at least at first sight, there is a definite analogy. One has to see how deep the analogy runs.
All right.
Michael, you had a question.
Yeah, I was thinking at a naive level of a magnetic analog of what you are describing. Yes. And Coriolis forces tend to create vorticity, and in a way they are analogous to magnetic field at a very naive level. But on Earth, you have the situation where the sign of the magnetic field changes.
Yes.
And that actually seems to induce an analog to a boundary.
Indeed.
Now, I did not chew through a situation where you have a varying magnetic field, where this effect is somewhat smeared, but may also have some manifestation.
So
the question is, can your discussion be carried also in the context of varying magnetic fields, in particular, one where you have change of sign?
So, okay, you can do the change of sign in two ways. You can do your mass in a situation where the magnetic field has a constant sign, in fact, is constant, and then another situation where it is opposite and equally constant. And the mass stops there, and then you just argue physically that if you put two samples next to one another where fields are different, sharply or gradually, doesn't matter, you will see interface states. But or you may want to carry out the analysis, the mathematical analysis, all the way to the end and look at the magnetic field which gradually changes. This I haven't done, but I presume it could be done. In this figure, what is illustrated in this figure is just you pretend that when you are at a point in the upper half sphere, you just see the tangent space, and there it has some positive value. And below, at the point below, in its tangent space, it has a negative value. And so if on the real sphere they meet somewhere, interface states must appear. But this is, this is a conclusion outside of the strict mathematics. But if one wanted, one could place it in that context too. Here I did something different. Rather than having two materials with different sign of F, I had just one material against the wall with suitable boundary conditions.
Yes.
But the other thing could be done too.
Interesting. Thank you.
Yeah.
I didn't think of that.
Thank you.
So are there any other comments?
Yeah, just one. So it was crucial that you had the product of I forget the numbers of the sign of your. It depended on the sign of the odd viscosity and the sign of the Coriolis force.
Exactly.
So that product had to be positive.
Yes,
But it was negative. Then you didn't. Then the Chern number becomes 0. Is that right?
No. So if it is positive, the Chern number is 2. If the product is negative, then the Chern number is -2.
Okay, and 0 is the point where it changes. You're saying
So when F is equal to 0, then the gap closes.
Right. Okay. Yeah. Okay. No, but yeah. Right.
Well, thank you, Gian Michele, for a really interesting and stimulating talk. I think we can applaud you.
Thank you, Arthur. Thank you, everybody.
And we look forward to one more seminar this year next week. Bye-bye. Bye-bye.
Bye-bye, everybody.
See you, everyone.
Bye, everybody.